Thank you very much for a very nice introduction. And yeah, it's a very nice feeling to be here and be able to present some of our work. It's a bit of a pressure being the first computational person. I didn't know that, so I hope I represent the field properly and yeah, don't bring sh too much shame to the computational people. So I will give a little bit of overview what we did over the last couple of years with our computational electrophysiology approaches, mostly focusing on potassium channels, but there are a couple of more general pointers at the very end. So let's hope we can get there. So this is so you of course most of you know what ion channels are. So this is actually more for my understanding or a reminder how I see ion channels, and probably I miss a lot of details. Um, but basically, what we are interested in is the gating of a channel, and then how the ions are passing in, and whether what are the mechanisms of ion selectivities in the channels that we work on. So really, those basic uh, atomistic single channel questions, if you wish. And then obviously we will have more and more interest in more applied parts. So we are interested in looking for computer for pharmaceutical tools to regulate the channels, whether we can use all the ever-growing toolkit of computational methods to design new drugs, new molecules, activators, modulators of ion channels, and so on. Quite a bit of interest is now in our lab also on the Herc channel. So this is a nice connection between kind of the basic questions we had on potassium channels before, now with a little bit more applied angle. So I will get back to this. So what we do in my lab, and still with in my previous place, so in Göttingen, with Bert de Groot. So he was one of the pioneer of this method that we now called computational electrophysiology. And then my idea was to kind of bring it and give it a little bit more to the scale, and try to establish it as a kind of complementary method to experimental approaches. So the idea is really simple. So we based on all our research on MD simulations, which gives you basically the dynamics of your atomistic system, and then we try to apply what is specific for ion channel research, which is the membrane voltage. We have two ways to do that. I'll spend some more time on it. And then if we're lucky and if the channel is open and it wants to conduct, we can see something like the movie on the right. So the ions are passing the channel, and if we simulate it long enough, we can count how many ions are passing through it, and that should, in theory, be the electrical current. So the idea of the lab is basically try to bridge the structural world of ion channels structures with their function that we can infer from electrophysiology, and see if we use these physics-based approaches on a single channel level, whether we see similar behavior in terms of current. And of course, if we were to simulate long enough, the channel should open and close. This is a little bit more difficult question because of the implied timescales, right? So the ions passing the channel should be fast, and usually we are lucky with this, and we can see quite a bit of events, whereas the gating is still a little bit more problematic. So yeah, so as I said, this is based on MD simulations. A little bit refresher what MD is. It's really a physics-based method that uses the Newtonian mechanics to predict the position and velocities of particles. In our cases, that would be atoms. To make them relatively fast, we do a couple of assumptions. So we rarely simulate the chemistry, so no bond breaking. Um, and we still, in most of the cases, use fixed charge models, uh, which can cause some issues with accuracy, but we'll also get back to it, hopefully. So of course, MD simulations is one of the biggest computational methods, has been used to many different systems. Some of them are shown here. Um, I feel like the transport processes are particularly interesting. Way back in the 2001, aquaporine water channels have been studied, and then some years later, ion channels also have been attacked with this method. So as I said, what is maybe specific, if we want to study ion channels in MD simulations, we need to actually observe a handful of ion permeations. We would like to have a way to apply the voltage in our simulations. And this is maybe not straightforward or not absolute. It's not a default thing. So there are two ways we can do that. One is the so-called single membrane approach or external electric field. So we basically apply a force to each charge. So each atom that has a charge, and basically almost every atom has a charge, and that would be the force. And this force will drive ion permeation. And then the theoretical work done by Benoit Roux mostly 15 years ago showed that this actually represents a correct description of voltage in an atomistic system. But it does have this a little bit of a sense of something artificial, because we just place the forces on the atom. So we have to be a little bit careful that this voltage we simulate is actually equivalent to the macroscopic voltage in experiment. Whereas another way of doing this is actually mimicking what is happening in the cell. So that would be placing two separate compartments so the ions cannot mix. So I should have mentioned in the single membrane on the left, what is the issue with this approach is, or something to keep in mind, is that in MD simulations we use so-called periodic boundary conditions. So the solution above the channel and below the channel is the same solution. So we cannot have different concentrations below and above the membrane in a simple way. So we are we have to use symmetric concentrations. Whereas if we apply in our simulation box two membranes, we can now play with the concentration gradients instead of applying the direct force on the charges. So we can have one compartment where the concentration of ions is different than the other one, and this will actually drive permeation and actually establish a voltage alike in real cell, where the difference in concentrations between inside and outside of the cell actually establishes the voltage. So these approaches are largely equivalent. As I mentioned, the single membrane, we typically can only use symmetric ionic conditions unless we use some additional tricks. And the permeation will be purely driven by the voltage, by this force applied to the particles. Whereas with the double membrane system, we don't know what voltage will be a priori. I mean, we can do back of the envelope calculations, but typically we have to set up a simulation, establish either the concentration gradient or actually the charge imbalance between the compartments. We can have asymmetric ion condition, and then we can have ion permeation that is driven by the concentration imbalance. So we can return to this later, whether these two ways of applying voltage are equivalent. One is maybe if we apply directly the force on the left-hand side, that would be more enthalpy driven, whereas we can have a system in a double membrane setup where that would be purely entropic driven, just because the concentrations are different. However, when it comes to the effect of the resulting voltage on the membrane or the energetics, let's say to the nucleation of a membrane, these two approaches are equivalent. When it comes to the permeation through the ion channels, it's actually not fully understood. So in our previous tests, we usually saw very similar behavior, but I believe there is still a little bit of research to be done. So this is maybe a little bit more realistic example what I meant by this double membrane system and what kind of simulations or experiments we can do, computational experiments, I should say. So we can have a one compartment that is purely that has purely potassium chloride, and the other compartment has purely sodium chloride, right? And then we can see um, how the permeation works, how the ions want to pass the channel, um, driven by so there is no charge imbalance, so to speak, because the number of charges is identical in both compartments, but of course the concentration for each ion is vastly different. And indeed, it worked in a way that we saw in this example. We saw permeation of potassium outward of the cell, uh, as it should be. Okay, so now going to the main part of the talk. So we apply these methods for potassium channels, and we work quite a lot on mechanism of how the ions are crossing the channel and how do they do selectively. So this high potassium selectivity for potassium over sodium uh, was kind of interesting to us. And then we have more and more questions about gating and whether the changes in the channel opening regulate the current and so on. So this is now a very old slide, so apologize to everyone who seen it multiple times. So we were kind of debating how the potassium is crossing the channel, and on one hand side we had this so-called canonical knock-on mechanisms where the potassium ions in the selectivity filter were separated by water molecules, whereas in our hands or in the hands of people in Bert de Groot's lab, even before I joined in 2014 13, they usually saw um, ions being grouped closely in the filter, so adjacent ions in the adjacent ion binding sites, no water separation, and no water co-permeation. Um, and we really wanted to know how it happens, and also interestingly, why different computational groups seeing different results, right? So this picture, the both of these pictures comes from simulations, and this is not a very good sign if computational people between themselves cannot agree what's going on, and it doesn't bring too much of a trust to the field. So we were on the mission to kind of understand what's going on. This is also a short reminder that the field, one of the issue or the problems when studying these potassium channels is that the filter itself is a gate. So it will be in the conductive state. So the ions in the filter will stabilize the filter in the conductive state, but at some point when there's fewer ions, the filter has a tendency to collapse. And then the question is always when it happens, is it a feature of the channel or is it a bug in a simulation that this collapse or this dilation happens too fast? So we were always on the side that on the time scales of our simulation, so let's say hundreds of nanoseconds or a couple of microseconds, the filter usually should stay conductive. Um, so we did a couple of years back, we did a little bit of a review to discuss different experiments, whether they were supporting one of the two mechanisms. And back then, that was the table we ended up with. So there were some question marks for both mechanisms in both cases. Um, but typically we could it was a little bit easier for us to kind of fit the direct knock-on mechanism with most of the experiments. But of course we came up with this mechanism, so we're a little bit biased. But at least we tried to write it in a kind of as much unbiased way as we could. So just a few examples. So this is also an old study now, but we were interested in once we had this mechanism, this direct knock-on mechanism that worked great in a symmetric potassium, we saw ions in adjacent sites. We were interested in if we could recover the selectivity of the channel, right? So we started simulating it now also with sodium. I think this is KCSA. but we did it for a couple of different channels. And when we started adding sodium, we kind of saw this dual picture where there would be periods when only potassium would be permeating relatively fast, and then sodium would bind to the selectivity filter, usually surrounded by two or more water molecules that would slow permeations for hundreds of nanoseconds, and eventually this sodium would need to be kicked out. So we repeated the simulations many times, and then we could kind of recover the ratios of sodium to potassium currents, and that's what on the plot on the left-hand side. So we were kind of in a back then we were in a kind of good ballpark. There is an issue with this study, but I will get to it very quickly. What was also nice, what we did here, which was actually suggested by a reviewer, was to say that we had this picture that it's this direct knock-on mechanism is working and it is selective in selective potassium channels, but there are also structures of non-selective channels. So the reviewer suggested whether we can explain that. So we simulated also this non-selective NAK to CNGN channel. And indeed, in our hands, it was non-selective. The ratios were kind of similar of potassium to sodium, and both of these ions were permeating with a lot of water molecules around them. So kind of the filter was quite different here. Was wider, was more had a larger plasticity, more dynamics. So that was all good, and back then, that was already many years back, we proposed this kind of mechanism of both permeation, direct knock-on ions in the adjacent sites leads to relatively high currents, and then occasionally sodium ions will block the permeation, but wouldn't be able to cross the channel, which kind of naturally explained the selectivity. Um, then we were challenged by some crystal structures that were meant to isolate separate states of the uh, soft knock-on mechanism or the knock-on mechanism. So with potassium separated by water molecules. Um, so that was interpreted in this study as a proof that the wild type channel conducts with water, because if you solve the structures of the mutants, they have water in the filter. So we simulated this as well and basically showed that well, the mutants do permeate the ions with water, but it's a very different mechanism, and it's very different from the wild type. But that kind of fit the experiments quite nicely in terms of the size of the currents or the reduction of the currents or the conductance that you can see here. But as I said, as I told you before, or I mentioned in the passing, there was an issue with all the studies that we did. So that was these studies were using the kind of out of the box force field. So the parameters used to describe the interactions between the ions and the water and the channel and so on. And in these force fields, so they will be shown here in orange and green, the conductance that we were getting to these channels. So here there are three kind of model channels that we use. The conductance simulated in our hands were order of magnitude lower than the experiment. So we were always mentioning this in the passing, and then our selectivity story didn't affect that much because the ratios between potassium and sodium were still right, but the absolute values for conductance, especially for potassium, was, as you can see, kind of order of magnitude lower than expected experimentally. So that was always kind of an elephant in the room that um, we had to address at some point, and kind of the explanation that we had back then was that the was related to what I mentioned in the introduction, that um, we use the fixed charges on all the atoms in our system, whereas in reality, uh, the instantaneous charges on the molecules will be different depending on the environment and possibly on the voltage as well, which especially if you have three or four potassium ions next to each other in the filter, that can change the rate quite a bit. So when Chengong joined the lab a few years back for his PhD, we wanted to have a little bit of a more high-level description of what is happening in the filter. So if you want to do that, you go to quantum mechanics, which again, you have the whole zoo of methods you can use in quantum mechanics, but in theory, you should have much more precise energetics of interactions, basically in any system. Um, but of course, this is very computationally expensive, so you cannot do it on the large systems. Luckily, in K channels, focusing on the selectivity filter itself is traceable, so it's not too big, and it's this core unit specific for all potassium channels. So that sounded like a good idea. So what Cheng-Gong did, he pulled the ions or one ion from one side to another in different configurations, and he did it on this blue level of theory. So that would be some DFT, and also with the force field that we used before, the green and the orange curve. So here is just the energy profile of this single transition of an ion from the side that is indicated. So as you can see, even with these ions being close to each other in DFT, on the DFT level, the barriers are relatively small, right? The blue curve remains flat, whereas the other curves show quite significant barriers of several kilocalories per mole, which would explain why the currents were so low. Um, and then around the time we were working on that, there was a little bit of a buzz in the model in the MD community about a cheap way of achieving some sort of polarization description by scaling the charges of ions. So instead of sodium or chloride carrying the native +1 -1 charge, there can be an argument made that maybe the descriptions in the systems that we're simulating, the description of 0.75 is actually more accurate. So since this is relatively easy to do, and this can be also treated even if we forget all the physics, it can be treated as a fitting parameter. So Cheng-Gong tried this with just scaling the charges of the ions, and then suddenly this free energy profiles look a little bit better when you compare the scaled force fields with DFT. So then we were like, okay, let's just see what happens if we simulate the ions, the whole channel with this scale force field. And suddenly we saw this, which was actually very close to the full occupancy of the selectivity filter with potassium ions, kind of resembling the first KCSA structures and all other potassium channel structures when they usually you see potassium next to each other, but it was interpreted for many years as being a superposition of two states, but perhaps it's not actually not. Perhaps it is for ions in the row, and this is what we are saying and seeing, and also the ions were actually crossing the channel relatively quickly, as you can see here. So there we were actually able to simulate these channels with two different force fields with different levels of scaling. And compare it with experimental currents, right? So these are full single channel IV curves, if you wish, for three potassium channels compared with experiments in black curves. And especially for this chart scaling factor of 0.78, so the green curves, we achieved quite a nice agreement with experiments, especially if you compare it with the blue curves, which were the previous non-scaled force fields, right? Which showed very low currents. Here we can see Pretty good agreement with experiments. Even for MTHK, we were able to recover this inward rectification, so higher currents are lower voltages, which was quite nice. Um, so this was good, and that worked. So this is only in symmetric potassium. And then back then we had this nice method that our force field should be, or that this direct knock-on was sodium selective. So the question was, is it still selective if we use our new scale force field? So the very naive approach actually showed the opposite. So the sodium started permeating better than potassium, which stopped the project for a couple of months because, well, this is exactly what you not want to have in a potassium channel. But then we realized that when you scale the charge of an ion, you make it effectively bigger. So the sodium becomes bigger than potassium, bigger than it just becomes bigger. So it becomes a little bit more like potassium. So you need to scale the radius of the ion, which is described by the so-called sigma parameter from Lennard-Jones interactions. And there's actually a very neat way how to do it if you consider the solvation-free energy. So you can make an argument that the solvation-free energy of an ion in the charge force field, the experimental value of the solvation-free energy should be scaled by the square of the charge of the scale charge. And then if you use this as your target solvation-free energy to reparameterize the ions, you actually recover you recover the correct radius of an ion. And then with these corrected ions, we look at the conductance again, and here the potassium conductance is still very close to the experimental one, but also at this scaling factor of around 0.78, we recover very strong potassium-sodium selectivity. If we then simulate our potassium channel with sodium only, symmetric sodium solution, we kind of get the density of sodium ions in the filter comparable with the previous reports, with the experimental data, which is actually quite nice. Is mostly, especially this sodium ion at S4 sitting in a planar geometry of the hydroxyl groups. So to summarize this part, we applied the charge scaling approach to develop new force fields for potassium ions and sodium ions, and tested it in different potassium channels. In all cases, we saw large currents comparable with experiments at the physiological voltages. All permeations were happening through direct knock-on, so 3 to 4 ions in the filter, and no water co-permeation. And we even reproduced this rectification behavior in MTHK, which was quite nice, which kind of came for free. So we are quite happy with this, how it works, and that the direct knock-on, that we saw this even more pronounced direct knock-on than we thought before. And then the question is, of course, is it real? So we were waiting for a long time for this paper to appear, and it finally appeared last year from Deka Hekstra from Harvard, I believe, when they used X-ray crystallography under electric field to actually directly observe selectivity filter occupancy under applied field. And here they concluded that this experiment supports adjacent ions, and that the selectivity filter is essentially fully occupied by potassium, also under electric field. So actually, the occupancy patterns here are very similar to what we saw in the simulation. So that all comes together pretty nicely. Okay, so I have bit of a time. So I promise you the Herc simulations. Once we publish the paper, or we convince ourselves that the charts, these new force fields are useful for model potassium channels, the idea was to try it for a more challenging one. And definitely Herc is one of the most challenging potassium ions to simulate, but of course also much more interesting. So whenever I started mentioning Herc, um, I got a lot of publicity, whereas when I was mentioning just MTHK of other bacterial channel was maybe not so interested. So Herc has been simulated before with classical force fields. However, very large voltages were used, up to 750 millivolts, and the large instabilities of the filter were detected. And then this discussion, there was this discussion whether this is, is this a sign of gating, inactivation, or is it something that Herc just does also during ion permeation? So I believe that the filter shouldn't change that much from the crystallographic one, at least for a handful of nanoseconds to support permeation. So we were just wondering if we apply this force fields that we came up with to Herc, whether we see a different picture. And indeed, we do see a different picture. So we see maybe fewer ions. So we rarely see four ions in the filter. We see a mixture of 3 to 2. But they still sit in the adjacent ion binding sites. We see ion permeation enough that we could recover some conductance. So we ramped the voltage to 300, which is on the high end, but still much lower than before. And the conductance that we see is on the order of the experimental one. And interestingly, we see this larger conductance at negative voltages, which seems to agree with some of the experiments done. So we call it asymmetric conductance. I don't want to call it rectification because in Herc, as far as I understood, rectification is usually explained by fast inactivation of the filter, which we also see, but I'm not going to talk about it right now. So I only focus on permeation here. So we saw this higher conductance at negative voltages. So we wanted to explain this. And one particular feature of Herc compared to regular potassium channels is that at the S4 position, it has a serine instead of threonine. And this serine is quite dynamic. So it can move a lot. And especially at plus 300 millivolts, the ion is actually very rarely seen at 300 at S4. So this occupancy plot on the right shows you that only maybe 10% of the time during the permeation, there will be an ion there. Whereas if we look at the inward permeation at negative voltage, the S4 will be occupied maybe 50% of the time. So based on these conductions, we kind of calculated the free energy profile of ion permeation, which shows this increased barrier for outward permeation. So that will be the blue plot around S4 and S cavity, and also looking at the distribution of the angles of the hydroxyl group of the serine. There will be a population where the hydroxyl actually not pointing toward the channel, so they cannot coordinate the potassium ion. Um, so we believe that this is kind of a reason. This dynamic S4 is a reason of this asymmetric conductance in Herc. Um, we also did a kind of Markov state-like analysis of different states during the permeation, and indeed the rate limiting step is the entry of ion to S4. Um, so basically, S4 will be occupied by water for a long time that can hydrogen bond with the serine, and then the ion at positive voltage has to find a way to kick this water out of S4 and enter the filter, and that would actually take a longer time. and that's why the outward conductance of Herc is so low. To test this, we mutated the serine to threonine, so to the classical, so the typically found amino acid in potassium channels in this position. And as you can see here, we eliminated this asymmetric conductance. So now plus 300 to minus 300 conductance is the same. The currents are still low, interestingly. The occupancy of S4 goes up in both negative and positive voltages. And it does increase the current for positive voltage, as you can see. So that kind of points out in the same idea that for the permeation of positive voltages, this geometry of the S4 is the rate limiting step, the entry of the ion. Whereas for the negative voltage, we actually decrease the conductance, interestingly enough. Um, but that kind of points out to this mechanism of, okay, I did. So this is an old slide, so I'm not saying this in the word rectification rather than asymmetric conductance, that this kind of wobbly S4 at positive voltages is the ion has to kick out the water molecule from there and enter, whereas at the negative voltages, because the ions be above S4 are kind of already in the queue, they will be kicked into the S4 much more easily. So that would kind of support why the current is higher at the negative voltages. And then very quickly, of course, we had this working Herc model, which was nice. We could see the stable filter, we could see ion permeation, currents, and so on. So then you want to actually start looking at the molecules, at the ligands, especially that this project is with Johnson & Johnson. So they are interested in whether we can predict cardiotoxicity. So first thing we did, there are crystal structures of Herc with blockers. So we use those, or we redocked these blockers to our open structure. They dock into exactly the same pose as found in the structures, which were nice. And then, of course, you simulate it with applied voltage, and you don't see any current because they sit below the filter. They are positively charged most of the time, and they really work as a kind of cork in a bottle and prevent any permeation. Especially outward permeation. I don't know how much of an on permission of simulations with negative voltage we did, whether at very high negative voltage the ions will eventually kick out the ligand out of the binding site. I think we never tried this, but that might be on the list. And then alongside we are starting to see if we can calculate the binding free energies, absolute binding free energies of ligands to Herc, and have also the angle of predicting whether a given ligand, a given drug, how strong it binds to Herc, purely from computational perspective, and then try to combine whether this delta G, so the binding propensity of the ligand also with the propensity of blocking the conductance. So you can imagine having a drug that can bind to Herc, but maybe it doesn't block it fully. So of course here we tested the method on the canonical blockers, so there is no current, but that was mostly to validate the method, which seems to reproduce what is known quite nicely. And then we moved to activators. So activators are much more interesting. So we wanted to see whether we can use this method, so combining Herc, structure prediction, docking, and simulations to see how these blockers are working, activators are working. So we were ending up with kind of two modes especially for this PD activators that we focused first, that either it kind of sits vertically below the filter or horizontally more in the pocket. So different tools have also different propensity for both. So we then started simulating them. And in our hands, we see currents and actually increased currents in this kind of horizontal pocket below the filter, where the drug seems to be quite stable, and there the carboxylic negatively charged group is the perfect position to actually support additional ion binding site, increase the local concentration of an ion below the filter if you wish, and increase the conductance by a factor of 2 or 3, um, which is quite nice. So this is fully computational prediction of the PD activators, of hERG activators effect on hERG activity. So the next step here will be to see if our method of predicting the binding affinity of these compounds works well, and then in the future to have a platform where for a given molecule one can predict how strong it binds to hERG, but also what is the functional effect. Does it increase the current? Does it block the current? Does it partially block the current, and so on? So kind of mixing the computational electrophysiology with free energy calculations. And I think with this I will stop. I think I largely overestimated how much time I would have. So here are some ideas that maybe we can use the computational electrophysiology to actually test the old electrophysiology theory. So maybe the GHK equation can be reconstructed or tested for a given channel purely from simulations with both different voltages and different concentration. But I guess that's a topic that could be a topic for a full next seminar. So with this, I would like to thank all the people that did a very hard job. So that would be my old lab colleagues and members in Göttingen, Bert de Groot lab, Andri, who was my first PhD student, Chengong, Rainier, and Tvard. They were PhD students that I co-supervised, and then people in London. So Ivan, Sophia, Sam, these are my PhD students, and I've been blessed with excellent collaborators, Vitas in Johnson and Johnson on hERG, Stephen Tucker and Markus Schewe on K2P channels, also on hERG, and Guillaume on K2P channels. So yeah, thank you very much, and I'm happy to take any questions.
All right, thank you for a wonderful talk, Wojciech. So for questions, please type them into the Q&A box, or if you'd rather ask your question in person, raise your hand and then we can make you a panelist. All right, so I'll start with this first question in the Q&A box from Damien Bell. Lovely data and modeling, Dr. Kopec, lab and collaborators. Sorry if I missed or if this is standard practice. With rubidium being well conducted, unlike sodium by potassium channels, can rubidium conduction recordings be combined with charge scaling to generate new models and MD simulations?
Yes, thank you. Thank you. Wonderful question. And the rubidium has been always on my mind, and also pushed by Markus that we can see here. So yeah, the effect of rubidium on many potassium channels is well documented, and for me still very difficult to understand. So this is definitely on the to-do list to come up with. So we tried some simulations with rubidium with the old force fields, and it was very inconclusive what it did. I think in most of the cases we saw a little bit of permeation, but lower than potassium. And definitely, I would be very willing to try it for charge scaling and see what it does, because yeah, absolutely. There's so much data of effect of rubidium activating the filter, stabilizing the filter, and I still don't know how it works on the atomistic level, and I really would like to know that. So yeah, thank you. Thank you. That gives me motivation to get back to this.
Marcel, go ahead.
Hi, Wojciech. Really nice talk. So I'm also curious about the charge scaling. In some of the
Mm.
plots you showed, it seemed like there was sort of a clear inflection point where you were hitting the right conductance, or maybe there were some other measures. And in others, it looked like you could sort of blow through it really quickly. And so I'm curious as to your thoughts on, is this something that you would have to sort of determine for each system, or are there principles you think we could arrive at the correct scaling so you wouldn't have to sort of determine it yourself for your own system?
Yeah, very good question. So we kind of we had like a mixed approach in here that so the theoretical argument is that the scaling should be around 0.775 for monovalent ions, and this is based on the I don't know where the equations are. So this is based on the argument that the we take the dielectric so the scaling factor should be 1 over square root of epsilon, and then we take the epsilon in the biological system will be, I believe, 2. So if you do the math here, the scaling factor should be around 0.75. So in most of the cases, this is what is recommended, and this is what works best. And that's why also here we kind of limited ourselves. Well, we tried what happens if you really overshoot it, but there is a theoretical argument to be made that it should be around 0.75. So this is nice that it kind of works here, but yeah, as you can see, for red curves you can overshoot it, which is not good. Um, this is most likely, this is still a hack, which works pretty nice. So it gives you this qualitative difference. But if you really would like to do the chart scaling properly, you would need to construct the force field from scratch. So here we take the old force fields, we don't touch anything, and we just scale the ions. So one can argue that this is valid in the first approximation, but to do it really correctly, one would need to construct the proper water model. One would need to construct the proper force field parameters for the protein that is compatible with that, and only then go with ions. So I believe this is the reason why um, it doesn't work perfectly. Well, it won't work perfectly because it's still kind of fixed charge model. But that was our motivation to test different scalings and kind of use different systems to see which one agrees well. The nice thing is that across 2 different force field families and 3 different channels, this 0.78 worked best in all of these cases. So that was still better than calibrating it every time for the new system. But to really do it properly, that would be like a proper constructing of a full force field from scratch. So this has to be still taken with a big spoon of salt, grain of salt.
So has another question.
One more question.
Go ahead.
Have you looked at chloride conductance for anything?
Chloride conductance. I believe there is some previous work done from Mark Sansom lab before he retired, and also Stephen Tucker was kind of continuing it a little bit. I think that was there were a couple of chloride channels, and I think they also tried this chart scaling. In our lab, we had a small project on CFTR, which is a chloride channel, but it was very difficult there. I'm not sure if the structure was actually open, but for actually this charge scaling and this polarization is even more interesting for anions, so for negatively charged ions like chloride, because they have a very interesting interactions with hydrogens. So with hydrophobic interaction with hydrophobic residues, which normally one don't think about because, well, it's an ion. It likes to be in water. It's charged. But since the hydrogens in all all hydrogens will have a little bit of positive charge. The interactions with the chloride will be different. So there are this funny interactions of chloride with hydrophobic residues, and I think that was at least in some of the papers from Mark Sansom lab, that was also improved with charge scaling.
Join me in thanking Wojciech, and we will see you all next month.